Good morning to all. Today we see the film conversion parameter and design of tower of fluid-fluid reaction. Okay. In previous lecture, we have seen the kinetic regimes of the fluid-fluid reaction, okay, and various cases in the kinetic regimes, and it is based on the type of the reaction: instantaneous reaction, fast reaction, intermediate reaction, slow reaction, infinite slow reaction. So cases A to H we have seen, and these kinetic regimes, okay, we have seen. Now this reaction where it is conduct means in the liquid film or main bulk of the liquid, okay. So in the liquid film, the reaction conducted of the cases A to H, A to D, instantaneous reaction and fast reaction. And already you have seen in the previous lecture the determination of the rate of reaction for the instantaneous reaction as well as fast reaction. Now for the intermediate type of reaction, there is a complex equation will be formed and there is a no derivation will be there, okay. So for intermediate reaction, the reaction will be happen in the bulk of the liquid as well as in the liquid film. Now for the slow reaction, the reaction will be in the bulk of the liquid, okay. And infinite slow reaction, this rate of reaction is depend only the reaction kinetic, not on the mass transfer, okay. Now this film conversion parameter, in this unit we see the to tell whether reaction is fast or slow, we focus on unit surface of gas-liquid interface. We assume that the gas phase resistance is negligible and we define a film conversion parameter as, okay. So this film conversion parameter means what? This film conversion parameter, it gives the reaction is fast or slow, okay. By this equation, this M, that is the film conversion parameter, and it is the ratio of the maximum possible conversion in the film to the maximum diffusion transport through the film, okay. So this M is the film conversion parameter we calculate by using mathematical equation. This is the K into Ci into Cb into X0. What is it? That is the maximum possible conversion in the film. Maximum possible conversion in the film means that is the whatever the A is entered in the liquid film, that will be react with the B and some conversion will be occurs, okay. This is called as the maximum possible conversion in the film, and this by the rate of reaction, that is the the K is the rate constant, K into concentration, okay, that is the K into Ci into Cb, okay. So that is Cb multiplied by X0. Why it is the X0? Because it is the this is the ratio and having the same unit, okay. That is the unit will be the surface, okay. So and maximum diffusion transport to the skim, that is the by Fick's law, okay. This D means suppose KL is the mass transfer coefficient, KL into Ci, okay. But this what is KL means DAL upon X0, that is the into CAR, okay. So this is the maximum diffusion transport through the film, that is the liquid film, okay. So A is diffused through this film, that is the X0 is the thickness. I think this X0 is the thickness of the liquid film, okay. So DL upon X0, that is the mass transfer coefficient. DL is the diffusivity, X0 is the diffusion path into Ci, concentration of A in the liquid film, okay, at the interface, which is equal to, now this X0 we can write here, that is the X0 square, and multiply and divided both sides DAL, okay, means denominator and numerator DAL. So K, so we write DAL square upon X0 square, this X0 right here, okay. So X0, this square will be here. So DL square upon X0 square means KAL square, correct. Ci will be cancelled. So what is remaining? K into Cb into DL upon KL square. This is the film conversion parameter, okay. And film conversion parameter, by this equation we get the film conversion by the value of this film conversion parameter, we get the we define the cases A to H. Okay, whether the reaction is a fast reaction, whether the reaction is slow reaction. Okay, so we see it where this, if MH is greater than 1, greater than 1. Okay, all reaction occurs in the film. All reaction occurs in the film means reaction occurs in the film. There is a no reaction occurs in the bulk of the liquid. Okay, if film conversion parameter is more than 1, okay, and surface area is controlling rate factor, when the reaction is occurs in the film, so surface area means whatever the area, the surface area in the tower, that will be the controlling factor. On the other hand, if MH is less than 1, means MS is less than 1, no reaction occurs in the film and bulk volume becomes the controlling rate factor, because reaction occurs, it is not in the film but it is occurs in the bulk of the liquid. Okay, so bulk volume is important thing. So more precisely it has been that if MH is greater than 1, film conversion parameter is greater than 2, reaction occurs in the film and we have cases A, B, C, D. A, B, C, D. A, B, these are the instantaneous reaction, and case C and D, this is for the fast reaction. So this reaction occurs only in the film. Okay, already we have seen in the kinetic regions. Okay, if MH is or film conversion parameter is in between 0.02 to 2. Okay, 0.02 to 2 means greater than 0.02 and less than 2. Then we have the intermediate cases, and these intermediate cases is the case E, F, and G. E, F, and G. Here the reaction occurs in a film as well as in the bulk of the liquid. Okay, and if this MH, okay, film conversion parameter is less than 0.02, then we have the infinitely slow reaction, and this infinitely slow reaction of the case H. Okay, so by this value of this film conversion parameter, we get where the reaction occurs and which case will be there. Okay, whether the reaction is instantaneous fast or intermediate reaction or infinitely slow reaction. If MH is large, we should pick a contacting device which develops or creates large interfacial area, because if for the large film conversion parameters and this reaction is occurs in the film, so controlling factor is only the surface area. So interfacial area, if it is a large, okay, then rate of this reaction will be the more. Energy for agitation is usually an important consideration in this contacting scheme. Okay, so the contacting device will be, should be picked up for the large interfacial area. On the other hand, if MH is very small, and MH is very small means then all the reaction will be occurs in the bulk of the liquid. Okay, means bulk of the liquid. So volume of the liquid is very important, because the volume of the liquid is a contacting is the controlling factor, and agitation to create large interfacial area is no beneficial. So this contacting device is not important, but is the bulk of the liquid is important in this case if MH is very small. For slow MH is very small means it is for the slow reaction. But MH is very large, then contacting device is important and interfacial area is important. Okay, so this is the film conversion parameter. Okay, so sometimes short notes may be asked, explain the film conversion parameter, or some MCQ types question will be there. Film conversion parameter equations and this region can be asked. Okay, so the kinetic regimes from solubility data. Solubility data means that is the solute is dissolved in the liquid. Suppose in absorption column, suppose ammonia and water is a mixture. So this ammonia is want to remove from the air, ammonia and air mixture. They are contacting with the water in absorption column. So ammonia is the solute and it is dissolved in the water, and it can be removed from the air. Okay, in the absorption column. Already you have studied in the practical of the mass transfer 1 absorption column. Okay, so in this case this ammonia is a solute and it is dissolved in the water. Okay, so what is the kinetic regime? So for this from the solubility data, so what is the equation? So we see this for reaction which occurs in the film, The phase distribution coefficient H can suggest whether the gas phase resistance is likely to be important or not. Okay, sometimes gas phase resistance is important or not, or liquid film resistance is the important. Okay, in the sometime. So to show this, we write the expression for straight mass transfer of A across the gas and liquid film. Okay, so this is the straight mass transfer. Only mass transfer is there. There is a no reaction. Straight absorption column. Only unit operation is there, not a unit process. It's absorption without chemical reaction and absorption with chemical reaction. There are two types of this absorption. So unit operation is the only physical changes, that is the absorption without chemical reaction. So this rate is minus 1 upon h dN upon dt, mass transfer rate, which is equal to 1 upon means or delta PA, partial pressure difference, divided by 1 upon kg plus HA upon KAL. Now this 1 upon kg means gas film resistance and HA upon KL, that is the liquid film resistance is there. This equation is generated from the solubility data, and this is from the interfacial mass transfer, interface mass transfer. Okay, so here from the solubility data we get the equation. Now here 1 upon kg plus 1 of HA upon KL. This 1 upon kg is the resistance offered by the gas film. Okay, and this HA upon KL, that is the resistance offered by the liquid film. So which one is the important? Is the gas film resistance is important or liquid film resistance is important for the controlling of the reaction? That okay, so this is the very important to identify if it is the gas film is resistance controlling or liquid film is resistance controlling. This overall rate of reaction is depend on this controlling steps. Okay, so this from solubility data, it is a highly soluble or low soluble. Based on this, we can provide the gas film is provide the large resistance or liquid film is provide the large resistance. Okay, so we see it. So now for slightly soluble gases soluble gases means HA means that is the Henry's constant. Okay, Henry's constant, this Henry's constant is large. Okay, because partial pressure, this suppose A is dissolved in the liquid, then partial pressure is equilibrium with the concentration, then PA is equal to HA into CA. Okay, so that is the, or at interface PAI, which is equal to HA into CAI. So HA is the, if it is the highly soluble gases, means HA is the large. Okay, HA is the large. Hence, with all other factors unchanged, the above rate equation shows that liquid film resistance term is large. Okay, liquid film resistance term is large. When any gas is suppose these two phases are coming in contact, gas phase and liquid phase is there, then solute is from the gas film is diffuse, very highly diffuse, and it is added in the liquid, and it is, if it is highly soluble is there, okay, then they highly soluble means what? This is the very large mass transfer rate to the gas film. So gas film is not a controlling step, but it is the liquid film resistance term is the, now liquid film resistance term is the large, and liquid film resistance term is the large means highly soluble is there. So this gas film so resistance offered by the liquid is less. So gas film resistance offered is the only here only one factor is remained, that is the gas film resistance, and they gave this rate of reaction is depend on only the gas film resistance. Okay, so the rate is controlled by the gas film. Okay, gas film because gas film resistance offered the high. Okay, and this gas film resistance controlled for the high soluble gases. The reverse hold for the highly soluble gases, thus we say that. Okay, so these slightly soluble gases, HA is large. Okay, hence with all other factors and above rate equations is that liquid film resistance large, means liquid film resistance controlled for slightly soluble gases. Okay, so this you must be remember these things. Okay, so this liquid film resistance control for slightly soluble gases, and gas film resistance control for highly soluble gases. For highly soluble gases means it is the, suppose solute is highly soluble in the liquid, means there is a resistance offered by the liquid is less. Only resistance offered by the gas film is the more. So gas film resistance control for highly soluble gases. and for slightly soluble gases, liquid film resistance is controlled. And remember this thing. This is a very, very important. Gas film resistance control for highly soluble gases and liquid film resistance control for slightly soluble gases. For highly soluble gases, HA is the small, and for slightly soluble gases, HA is the large. Okay, so remember this. Now we say the design of the tower. Okay, so this design of the tower for fast reaction with respect to straight mass transfer without reaction. Okay, so in this design of the tower fast reaction, see this tower. Okay, gas is passed from the bottom of the tower and liquid is passed from the top of the tower. Now here this tower is only straight mass transfer without reaction. Okay, so this is the straight mass transfer without reaction, no chemical reaction is there. Okay, so this is the gas. Okay, now high partial pressure of A at the bottom side because the gas is passed from the bottom. Okay, gas is passed from the bottom and it is leaves at the top. The high, that is the concentration of A, means solute is present. That is the high partial pressure of A, and it is a low partial pressure of, because solute is dissolved in the liquid, coming in contact with the liquid in the tower. So from the top of the tower, this liquid, okay, this non-reacted liquid is passed, okay, from the top, and this concentration Ca we measure, concentration of A at the top, and from the bottom, that is the high Ca. This is the low Ca and high Ca, because solute is here diffuse in the liquid or soluble in the liquid. So high Ca will be, okay, will be there, and this 1 and 2 we consider. So what is x1 y1 x2 y2? Okay, these are the ratio, solute ratio to the inerts. Okay, ratio of the solute to the inert. Okay, so this is the interface mass transfer, gas beam and liquid beam there. Then Pa is diffuse. Pa is diffuse, and PAI is measured partial pressure of A, partial pressure of A, okay, at the, okay, so this CAI, that is the concentration of A in the liquid film at the interface, and Ca is the concentration of A in the bulk of the liquid. This is the gas side and liquid side. Already we have seen in the interface mass transfer, and this is in the design of the tower absorption column. Same way we see here. C is the molar flow rate of the inerts in the gas, and L is the molar flow rate of inerts in the liquid. Okay, G and L. Okay, so this, now we see the material balance over this tower. Okay, and we consider suppose small section, and H is the length of the tower. Okay, suppose Y is the moles of A in the gas divided by moles of inerts in the gas. X is the moles of A in the liquid divided by moles of inerts in the liquid. Now take the material balance of A over the tower. So this input we take G into Y1. G means that is the inerts flow rate. So multiply by this inerts. Y is the moles of A. So at input A plus input A in the liquid, okay, that is the L into X2. Okay, this inerts will be cancelled, multiply by L and moles of A in the liquid. Okay, which is equal to same way output G into Y2 plus L into X2. Okay, so solute in the gas plus solute in the liquid input, which is equal to solute in the gas plus solute in the liquid at output. Okay, so rearrange this equation. G into Y1 minus Y2 is equal to L into X1 minus X2. We get it. Means G into Y1 minus Y2, that is the difference. G into dy, which is equal to L into dx. That is the equation number 1. This is the material balance equation. All of you know. G into dy means that is the this Y1 minus Y2, this difference input to output, means that is the number of moles of A is lost by the gas, and this x1 minus x2, okay, or x2 minus x1, that is the dx, means that is the number of moles. This difference means some solute is added, means that is the A is gained by the liquid. So A lost by the gas is equal to A gained by the liquid. Now this equation, this is the in terms of molar ratio. Now this equation we convert into the partial pressure and concentration. For the gas side it is the partial pressure, and for liquid side it is the for liquid side it is the x, okay, and concentration in terms of concentration. Suppose if pi is the total pressure in the tower and Ct is the total concentration, then this equation we can write G into pi into dPa, means convert this by molar fraction and using the this total partial pressure which is equal to total pressure into mole fraction. Okay, so this we can convert pi into dPa upon pi minus Pa square is equal to L into Cq dCa upon Ct minus Cs. Similar way, partial concentration which is equal to total concentration into mole fraction. Okay, same way. So here this equation, above equation, we can write differentiation of G dash into Pa upon pi. Pa upon pi, that is the x, okay, and L dash into Ca upon Ct. What is Ca upon Ct? That is the x. This is Pa upon pi is the y, and Ca upon Ct is the x. Okay, is the ratio. Okay, molar ratio. Okay, same. So, but G dash and this L dash here, and G and L. Okay, where this G and G dash is the nearly equal, because why? For dilute solution, when Ca is less than Ct, Ca is less than Ct, and Pa is less than pi. Okay, this for dilute solution. Okay, means very less concentration. So as partial concentration as compared to total. Okay, so this pi minus Pa means what? This difference is nearly equal to pi, and Ct minus Ca is nearly equal to Ct. So L is nearly equal to L dash and G is equal to nearly equal to G dash. This is for the inerts and this is for the total. Okay, so we can write G upon pi, G upon this, G upon pi is the total into dPa. Okay, dPa, which is equal to this L upon Ct. This is Ct total concentration. So saying Ct is constant into dCa. Okay, so this in terms of partial pressure and concentration, this equation, balance equation, will get. Equation 2. Remember this equation, G upon pi into dPa, which is equal to L upon Ct into dCa. Okay, so G into dy, which is equal to L into dxa, which is equal to G upon pi into dPa, which is equal to L upon Ct into dCa. This is the equation number 3. Okay, so this is the equation number 2. Means this equation 1, that is the G dy is equal to L into dx. Okay. This convert into the partial pressure and concentration. This equation we get G upon pi into dPa, which is equal to L upon Ct into dCa. Okay. Now using this equation for tower design. Okay. Rate of reaction we find out at any point in the tower. The transfer of A per unit surface of interface is given by transfer of unit per unit interfacial area. That is the rate in terms of per unit, that is minus Ra is equal to minus 1 upon S into dNA upon dt. Okay. Okay. So this minus Ra is equal to minus 1 upon dNA upon dt. From the above equation, this rate we can find out by this interfacial mass transfer, that is Kg into Pa minus Pi, which is equal to Kl into Ci minus Ca. Okay. So this equation. So this equation Kg into Pa minus Pi is equal to Kl into Ci minus C. Okay. So what is G or IL? This is the moles of A reacted per unit cross section area of the tower per unit time. That is the molar flow rate. Okay, molar flow rate. Okay, moles of A reacted per unit cross section area of the tower into time per time. Okay. What is the Ra? Ra is the moles of A reactor. That is the rate of moles is the moles of A reacted per unit interfacial area per unit time. Okay. Now we have G and this minus Ra. If we earlier equation, this equation 3, in this equation, G and L in terms of this equation, equation 3, and this minus Ra dash. Okay. So we want to equating these two equations. So equating, but these units are different. Okay. Moles of A reacted per unit cross section area of tower per unit time. Here moles of A reacted per unit interfacial area per unit time. So here cross section area of tower and here interfacial area. So this is this. Okay. So this unit moles of A reacted per unit interfacial area per unit time. Okay. So this interfacial area convert into the cross section area. Okay. Cross section area of tower. So interfacial area upon volume of tower means that is this interfacial area per unit volume of tower, that is the AI. It is denoted by AI, and this is denoted by minus RA, this minus RA there. Okay, so this AI multiplied by height of the tower. We take the section of this tower. Okay, then that is the DH. Okay, why it is the height of the tower? Okay, this is the volume of tower, and volume of tower means it is the cross-sectional area of tower multiplied by height. Cross-sectional area multiplied by height. So height will be cancelled. This cross-section area is there. Interfacial area is cancelled. What is the remaining? Moles of A reacted per unit cross-section area of tower in per unit time. Means minus RA double dash AI into DH, which is equal to, means this unit is remaining, which is equal to, that is the G, moles of A reacted per unit cross-section area of tower per unit time. So G reacted means that is the G into dy, correct, which is equal to L into dx. That is the equation 4. Okay, so from equation 3 and 4 we obtain this minus RA into AI dx is equal to J upon pi into dPA. Okay, dPA, correct, or this L upon CT, which is equal to dCA, correct. So this equation, now what is minus RA there? This minus RA means kg into PA minus PI equation, this equation minus RA. Okay, so this equation so first of all we solve for this only for the gas form. So kg into PA minus PI into AI into DH, which is equal to J upon pi into dP. So DH we calculate here. Okay, DH. So DH is equal to G upon pi into dPA upon this rearrange equation, pi into kg into PA minus PI. Okay, pi into kg into this AI. Okay, into dP upon PA minus PI. In the previous lecture we have seen this kg into AI means what? That is the volumetric. It is depend on the volumetric mass transfer coefficient. Okay, so this H. Okay, so this DH is equal to J upon pi into kg into AI into dP upon PA minus PA. Now integrate this equation. This is the DH small section of the tower, and summation of all this DH, that is the total height of the tower, that is H is equal to G upon pi into kg into AI integration from PA1 to PA2, from PA1 to PA2, from bottom to top or top to bottom, depend. So PA1 to PA2 into dP upon PA minus PI. This is the equation, height of the tower, and this is for the gas beam. Now for the liquid beam, same equation. If you solve for the liquid beam, minus RA into A into DH, which is equal to, that is the CT, CA upon C, L upon CT into DC. Solve this equation for the liquid beam, and we obtain this H is equal to L upon CT into KAL into AI integration from CA1 to CA2 DC upon CAI minus C. So this equation is for the calculating height of the tower. Okay, for straight mass transfer for absorption. Okay, there is no chemical reaction. If there is a chemical reaction is there, okay, design of tower for fast reaction for mass transfer with reaction is another derivation. Okay, so design of tower for fast reaction for mass transfer with reaction. Consider the reaction is this: A plus B to give the product. A is the gas, B is the liquid, and the small b is the, what is small b? That is the mass stoichiometric coefficient. So material balance for the tower we take this same procedure we applied. So PA1 partial pressure of A, input in the gas, PA2 is the partial pressure of A, output is the gas. Now here reactant liquid is there. Okay, so this reactive liquid, that is the CB1 concentration of B at point 1 at the bottom of the tower. Okay, at output. Okay, CB1 concentration of B and CB2 concentration of B at input in the liquid. Okay, so these both are reactive. A and B are reactive. Okay, and reacted to each other, and it is consumed, and then product is formed. So A lost by the gas. A is lost means react with the B. Okay, B is also lost. So B lost by the liquid means that is the rate of reaction of A, which is equal to rate of reaction of B, and it is the equating by this stoichiometric coefficient 1 upon B. Okay, that is the minus RA is equal to minus RB upon B. Same way, A lost by the gas equal to 1 upon B into B lost by the. So G into DYA So material balance equation, we take the material balance equation. So previous derivation, we calculate the material balance. G into dy is equal to, that is the L into dCA. But instead of dCA, we using here B. Remember this concentration of B here. So G d into dy, which is equal to, how it is equating? That is the 1 upon B. So minus L upon B into dxB, because it is a counter current operation. Okay, counter current operation is minus sign will be there. So G into dy is equal to minus L upon B into dxB. So D into G dash, what is this? We write, okay, earlier you have seen G dash into dPA upon pi, okay, which is equal to minus this 1 upon B into D into L dash into CB upon CT, correct? So this ratio means that is the XB, this ratio P upon pi, that is the Y, okay? So G upon pi, G dash is nearly equal to G and L dash nearly equal to L, means G upon pi into dPA, which is equal to minus L upon B into CT into dCB. This is a with reaction, mass transfer with reaction. In earlier derivation, there is only G upon pi into dPA, which is equal to L upon CT into dCA. In terms of A is there. Now here A and B both are there and both are reactive. So G upon pi dPA is equal to minus L upon B into CT into dCA. Why minus? It is the opposite directions. Flow is the opposite direction. Okay. So this equation 1 we obtain. Similar way, this is the, if you plot x and y, we obtain this operating line. The slope of operating line, this is counter current operation, minus L upon B into G. Okay, and then for co-current operation, in the same direction flow both gas and liquid, then we operate, this is the plus operating line, slope is the plus L upon B into G. Okay, now the height of the tower is found by combining the rate equation and material balance for a differential element of tower volume as shown in the figure. So suppose this is the tower, dH is the height of the tower, input of the gas Y plus dy, output is the Y difference of this, and input is the xb plus dxb, and this is the output is the xb. Okay, for material balance, that is G into dy is equal to minus L upon B into dxb, their material balance, which is equal to modes of a reactor divided by interfacial area into time into interfacial area upon volume of unit volume multiplied by height of the element. Okay, so means this is earlier we have seen how to equate it, which is equal to minus RA dash into AI into DH. Okay, so this equation means, so we obtain this and solve this equation. So H is equal to G into integration y this minus RA we cannot write directly now. Okay, because it is the reactive type, and for the reactive time we cannot write this. In earlier derivation there is a straight mass transfer, so interfacial mass transfer rate we can write. Okay, so minus R is equal to kg into pa minus pi. Okay, so this equation we write, but in here this minus RA we determine by the case A, B, C, D, depend on the rate of the reaction. Okay, so this case A, B, C, D that will be applied here. Okay, now so by this way you calculate the rate of reaction. Okay, so H is equal to, now this interior in this equation, that is H is equal to this G. Okay, G integration from y1 to y2, dy means dy divided by this minus RA, we write this minus RA into AR. Okay, so this H is equal to G into integration y1 to y2 dy upon minus RA into AR, which is equal to L upon B integration xb to xb1 to dxb upon minus RA double dash. So this equation is using for calculating the height of the tower for chemical absorption straight mass transfer with reaction. Okay, sometimes these two derivation may be asked in the examination without reaction and with reaction mass transfer. Okay, so remember this equation. So this equation, final equation, that is H equal to G upon pi integration P1 to Pa2 dPa upon minus A in terms of partial pressure. Okay, and in terms of concentration in the liquid film, H is equal to L upon B into Ct integration from Cb2 to Cb1 dCb upon minus Ra into AR. Okay, so this equation will be obtained. Okay, so this is for gas film and this is for the liquid film mass transfer with reaction. Okay, so this equation we obtain. So earlier these important questions are there. Explain the film conversion parameter. That is the important. Already we have defined the N value, and based on this N value we can where the reaction is occurs in the film or in the bulk of the liquid. Now second question is there, derive the equation of height of the tower for fluid reaction with respect to mass transfer without reaction. This is important, mass transfer without reaction, calculate the H. Okay, okay. So this H in gas beam and liquid. So derive the question number 3, derive the equation of height of the tower of fluid reaction for mass transfer with reaction. Okay, so without reaction and with reaction, you must be explain this H. Okay, so this H derivation will be the height of the tower we can calculate. Okay, so these are the important questions asked. Okay,